Hello friends, welcome to the course Essential of Data Science with R Software 1, in which we are trying to understand the basic fundamentals of probability theory and statistical inference. So now you can see we have now understood about the role of probability in computing different types of tools for the statistical inference. So now I ask you a very simple question. In case if somehow it is becoming difficult to compute the probability from a given PDF or PMF, what do you do? Can you recall that when we had discussed the normal distribution, then we had computed different types of probabilities. How? Just by taking the random variable minus its mean divided by standard deviation. And we had seen that that was a good approach to find out different types of approximations for the probabilities which are coming from different distribution, either discrete or continuous, but they can be very well approximated by the normal distribution. So now in this class today, in the lecture today, I will be working on this concept. And we are going to talk about a very important result. This is central limit theorem. Well, if you come to the pure statistics, there are several forms of the central limit theorem which are defined for different types of conditions. Here in this case, I am going to discuss the most simple form of the central limit theorem, and I will try to illustrate that how much it is useful in real data applications where you are trying to find out the value of approximate probabilities using the normal distribution. So let us begin our lecture. Okay, so what is this central limit theorem? In a very simple language, I can say that the central limit theorem tells that the sum of a large number of independent random variables has approximately a normal distribution, right? And it gives us a very simple method for computing approximate probabilities for the sums of independent random variables. You can recall that at couple of places I had shown you that okay, if two random variables are independent, then their sum also has got a probability mass function or probability density function with some specific parameters, and then in case if you want to find out the probabilities of their sum, that means you have to first compute their joint probability density function of the random variable x1 plus x2, and then you have to find out the probabilities from there, which is many times difficult. So the central limit theorem helps us and explain the fact that the empirical frequencies of so many natural population exhibits a bell-shaped normal curve. Right, that is a very useful information for those who are working in real data applications, right. So there are various forms of the central limit theorem, and we consider here a very simple form, right. So this theorem says that let x1, x2, xn be a sequence of independent and identically distributed random variables, and each of this variable is having a mean mu and variance sigma square. I am not assuming any distribution, or even I am not saying that whether x1, x2, xn are say discrete or say continuous. Now, for large n, the distribution of x1 plus x2 plus xn is approximately normal with mean n times mu and variance n times sigma square, right. Then it follows from the central limit theorem that x1 plus x2 plus xn minus its mean n mu divided by its standard deviation sigma into root n, this will approximately follow a normal distribution with mean 0 and variance 1. That is your standard normal distribution. And now you can see here, if you can just write down this thing as say x1 plus x2 plus xn divided by here n minus here mu, then what will happen? This result will be converted into a sample mean x bar n. So now both the options are there, and I will try to explain you. So now at in case if you want to find the probability that x1 plus x2 plus xn minus n mu divided by sigma into root n, this is less than some quantity say x, then finding out this probability might be difficult, but you can very well approximate it by the normal 0 1. So, this can be approximated by probability that z is smaller than x, where your z is standard normal variate following normal 0 1. Right. So, this result can also be expressed as the distribution of say here z n, which is x bar n minus mu divided by sigma by root n approaches to normal 0 1 as n approaches infinity. Right. So, now you can see here in this result, nowhere I have assumed that x 1, x 2, x n are continuous or discrete, but we are saying that this result is valid for actually both, right. So, this x 1 plus x 2 plus x n minus n mu divided by sigma into root n, or say x bar n minus mu divided by sigma by root n, their distribution is always going to be continuous, which is normal 0 1, and normal 0 1 is a continuous distribution. Right. And beside this thing, if you have observed it, nowhere I am saying that x 1, x 2, x n they are coming from binomial or Poisson or exponential or geometric. We have not talked about it. So, nothing is said about the form of the original density function. The only thing what we are trying to assume, that we are assuming that the variance is finite. So, whatever the distribution function be, provided that provided only that it has a finite variance, the sample mean will have approximately the normal distribution for large samples. Yeah, that is the condition, that for finite sample the approximation may not be good, but as you try to increase the value of your sample size or n, this approximation will become better. Right. Now, in case if you ask me that you are assuming here that the random variable should have finite variance, do you think that is it a very difficult assumption? Whatever distributions you have done up to now, when you have seen that they had finite variance, and similarly if you try to look for other probability distribution, then most of them have finite variance. There is only one distribution, Cauchy distribution, which has this problem, that it does not has the finite variance, but for all other things there should not be any problem. So, the condition that the variance be finite is not a very critical restriction, so far as we are concerning the applied statistics, because in almost any practical situation the range of the random variable will always be finite, and in that case the variance must necessarily be finite, right. So, this is not a very difficult condition. So, it is not a very stringent condition that cannot be satisfied in real life. So, we need not to worry that much, and it will give us a good result. So, now let me try to demonstrate that how this result will look like by taking an example of exponential distribution. Now, you know what is exponential distribution. So, let x 1, x 2, x n be a sequence of IID random variables from exponential distribution whose PDF is this as and is having a parameter lambda. So, each of this xi has mean 1 upon lambda and variance 1 upon lambda square. So, now I can say that if I try to consider here this quantity here x 1 plus x 2 plus x n minus n times lambda divided by the standard deviation, that is square root of n upon lambda, then for large n this will have approximately a normal 0 1 distribution. So, now I will try to demonstrate this result using the R software, so that I can show you that how it look like. So, what I am going to do here, that I will try to generate the samples from this exponential distribution with say lambda equal to 2, and then I will try to compute the sum x 1 plus x 2 plus x n, and I will try to compute this quantity also, that x 1 plus x 2 plus x n minus n lambda divided by square root of n divided by lambda. And now I will try to repeat this experiment, and every time I will compute these two quantities for a given sample, and then after that I will try to create a density plot of both the values which are obtained for this and this, and we also try to find out their mean and variance, right. So, it is not difficult. I am now giving you here the entire program. You have the slides also, so you can simply copy and paste this program and you can just do it. So, you can see here this program is pretty simple. We have only here the number of observations and the number of times we want to repeat it, and then I am trying to generate the observation from this exponential distribution using the command n lambda that you know, and then I am trying to compute their sum, and then sum minus n lambda, and then square root of n divided by lambda, right? And then whatever is the outcome I am trying to use here in plotting the density curve, and this is the screenshot, right? So, well, my basic objective is to make you convinced and to show you that how these things are happening. So, now we try to generate the number of observation as say 10, 100, 1000, 10,000 from exponential with lambda equal to 2. And then we change them up to n observation plus rep. Rep means repetition. So, this n is going to be increasing, right. So, we start with n and then continuously the n is going to be increased, and every time these two quantities their sum and then this quantity sum minus n lambda divided by square root of n lambda, this is going to be calculated, right. And then means I have plotted all this curve clearly here. So, now you see that is the outcome. So, when I try to take out here this 10 observation, then the plot of the sum, that means x 1 plus x 2 plus x n, this looks like this one. You can see here the curve. And if I try to plot this central limit theorem, that sum minus its mean divided by standard deviation, it looks like this. But now, in case if I try to increase the sample size, right, I try to increase the samples from 10 to 100. You can see here now try to compare this curve and try to compare this curve. What is really happening? This is becoming smoother, but this is now becoming more symmetric. And in both the cases, if you try to see here that means and variance are obtained here like this, right. And here even you can see that the mean is coming out to be say minus 0.22, which is say means quite close to 0, but still that is not actually 0, and variance is not actually here 1, right. But if you try to increase the sample size, the mean and variance are going closer to 0 and 1 respectively. Now, in case if you try to increase the sample size to 1000 and then to 10,000, then the density plot of the sum will look like this or this. But in case if you try to plot the sum minus its mean divided by standard deviation, that is CLT, it will look like this. And you can see here that as n going to infinity, this curve is becoming more symmetric and more similar to the normal density curve, and even the mean and variance they are approaching towards 0 and 1 respectively. Okay, so this is the basic idea of the central limit theorem, and you can see here these are the results which I have reported you here. Right. Now, do you remember that when we did the normal distribution, then we also had discussed this aspect, continuity correction, and there I had explained you that when we are trying to approximate a discrete distribution by a continuous distribution, then there is a need of continuity correction, and I had explained you what is this, how it is obtained. So, now I will not explain it again, but I will try to use it here, because in the central limit theorem also when you are trying to approximate the probabilities for a discrete random variable, then you need to apply the continuity correction also. Right. So, and we approximate the probabilities for discrete distribution, we incorporate the continuity correction also, right. So, let x 1, x 2, x n be a sequence of IID, but discrete random variables, and each having a mean mu and some variance a sigma I square. Suppose we want to find out this probability that x 1 plus x 2 plus x n, they are lying between two numbers x 1 and x 2. So, now I have to do the same thing that we discussed earlier, that I have to subtract 1 by 2 in x 1 and I have to add 1 by 2 in x 2, and then I will try to compute the probability after standardization, right. What we try to do, we try to simply write down here x 1 plus x 2 plus x n minus n mu divided by sigma root n, and the same thing I try to do on the both the sides, and this probability can be obtained the probability of here this quantity minus probability of here this quantity, very straightforward algebra that now you know, and this is nothing but this can be obtained by the CDF of normal 0 1, and this is also the CDF of normal 0 1. Right. So, both these probabilities can be obtained at these 2 points, x 2 plus 1 by 2 minus n mu divided by sigma into root n, and x 1 minus 1 by 2 minus n mu divided by sigma into root n. Right. So, now let me try to give you here one more example from the Poisson distribution, where we try to apply this continuity correction. So, let x 1, x 2, x n be a sequence of IID random variables from Poisson distribution, each having a mean, say lambda is equal to 0.125 and variance is equal to 0.125, because in the case of Poisson distribution the mean and variance both are the same, and its probability mass function is given by this quantity. So, for example, if I try to say here, therefore, n equal to 65, suppose we want to know the probability that sum of this xi is equal to 10 is equal to 0.099, right, that we can obtain in the R. Now, we try to approximate the same probability using the central limit theorem. So, what I try to do here, that I try to write down here summation I goes from 1 to n xi equal to 10, and this can be obtained by applying the continuity correction, that you try to say subtract 1 by 2 and add 1 by 2 on the left and right hand limits, and then you try to standardize it. That just means summation xi minus its mean divided by standard deviation, and you get here this expression, and this probability can be written, because now this is here your here z, that is the standard normal variate following a normal 0-1 distribution, and this probability can be written in the form of CDF as CDF at this point and the CDF at this point, right. And if you try to compute this probability from the R software, this will come out to be 0.108. This is not difficult at all, right. So, now in case if you try to take here, suppose here n is equal to 96, and you try to compute the probability that summation xi is equal to 10, this will come out to be 0.105. But if you try to use it on the basis of say a central limit theorem, this will come out to be here 0.101. So, you can see here this is more closer to 0.105 than the case when we had n is equal to only 64, right. So, you can see that as you are trying to increase the sample size, the probabilities are becoming more clear. Okay, so, now we try to come to one more result, where I am trying to give you the approximate distribution of the sample mean, because now in the last lecture we have seen that sample mean is playing a very important role when we are trying to draw different types of statistical inferences. Right. So, let this x1, x2, xn be a sample from a population having a mean mu and variance sigma square. Now, the central limit theorem can be used to approximate the probability distribution of the sample mean, say x bar n, which is equal to 1 upon n summation I goes from 1 to n xi. Now, we know, we already have actually proved that expected value of x bar n is equal to mu and variance of x bar n is sigma square upon n, which depends on this here n. And we also know that this x bar n, this is based on a linear combination of the normally distributed random variable. So, when sample size is large, then x bar n minus mu upon sigma by root m, this will also have an approximately normal distribution with mean 0 and variance 1, that is the standard normal distribution, normal 0 1, right. So, now let me try to give you an example of this result. Suppose the height of university student was measured, and it was found that it has got a mean of 167 centimeter and standard deviation of 27 centimeter. Now, a sample of 36 workers is chosen from that population, and we want to find the approximate probability that the sample mean of the height lies between 163 and 170. That is what we want to find out. So, now using the standard notations, let z be a normal 0-1 random variable, and it follows using the central limit theorem that x bar is approximately normal with mean 167 and standard deviation 27 divided by the square root of 36, which is the value of here n equal to 36, and this will come out to be here 4.5. Now, in case if you want to compute this probability that x bar is lying between 163 and 170, you can just standardize the sample mean by writing sample mean by minus its mean divided by standard deviation, and you try to do the same operation on both the sides, and you can simply solve it. After this will become a standard normal variate, and this probability will be equivalent to finding out the probability between minus 0.8889 and plus 0.8889. So, you have done a result that probability that z is lying between minus a and plus a, right. Then this can be written as say twice of a probability that z is less than a minus 1. So, I can use that result over directly here and can find out the value of the CDF at this point from the R software. So, that you know how to find out the value of the CDF in the standard normal. distribution. So, this value comes out to be here 0.625 and so on. So, you can see here it is not difficult to obtain such complicated probabilities without any problem. Now, let me try to address the last topic of this lecture, that many times in real life we always have a question that what should be the sample size, means how many observations should we draw so that we can take a reasonable conclusion. So, now the question I am trying to phrase here is that how large the sample size and needs to be for the normal approximation to be valid. For example, in all these cases we are trying to approximate the probabilities using the normal distribution, and we are saying at least theoretically that as n goes to infinity this will work, but in practice somebody will always like to know what is this n for which it is really going to work. So, this answer depends on the population distribution of the sample data that is there, that you have seen. Means I was always trying to do an experiment and I was trying to show you the results after every probability density function and probability mass function, that I would try to generate the observation from that distribution and then try to compute its mean and variance. And then I was trying to show you that as n is increasing, the estimated value of mean and variance are converging towards the theoretical mean and variance, right. So, now for example, if I say the population distribution is suppose normal, then the sample mean will also be normal regardless of the sample size, then there is no issue. A general rule of thumb is that one can be confident of the normal approximation when the sample size is n is greater than 30. Now, you know what is the reason, means this reason will become more clear as we move forward, but do you remember the discussion in the T distribution lecture? Try to think about it. So, in such a case, even if the underlying population distribution is not necessarily normal, the sample mean of a sample of size at least 30 will be an approximately normal, right. And the normal approximation is valid for much smaller sample size in most of the cases, but it depends on say different types of parameters which you are going to involve, or what is the probability density function, probability mass function and so on, right. So, now let me come to an end to this lecture. That was a very short and simple result. But what I am trying to address here, that is very important, because in data science you are dealing with complicated distributions, and sometimes there can be a combination of discrete as well as continuous random variables also, and you are always interested in computing different types of probabilities. Well, without probabilities you cannot do the statistical modeling, that we have understood. So, now whenever you are trapped, whenever you want to find out the value of the probability, yes, you cannot find out the exact probability, but if you try to use this central limit theorem, possibly you will get a very good approximation, and this is going to work very well in practice. Now, regarding the sample size issue, my experience says that the sample size required depends on many things. For example, even if you are trying to take the normal mu sigma square, in case if the sigma square value is very low, possibly you will need a smaller sample size. But in case if your sigma square is very high, then you will need a much larger size. So, the same thing can happen in other type of probability density functions also. Also, in real life, whenever you are trying to deal with the real data, it may be difficult many times to know exactly what is the probability density function or probability mass function. So, you are simply trying to approximate or assume that this is the distribution which is going to represent the true data up to a great extent. So, that is a sort of approximation. So, under those type of situation, this CLT is going to help you a lot. So, now I will stop here and I will request you that you please try to think, try to look into books, and you will find different versions of the central limit theorem under different types of conditions. For example, here we have assumed that that the random variables are identically and independently distributed. Suppose they are not independent, then these results are not going to be valid. So, for that you have to look into the books and find out the correct version. But now I am sure that after so much of training, it should not be a very difficult task for you to learn and understand those things. So, you try to revise, have a look, and I will see you in the next lecture with more topics. Till then, goodbye.